Hello. In this presentation, I will discuss my project titled Neural Heterogeneity for Task Compartmentalization. This work was done by myself, Chetan Dulipala, and my professor, Dr. Shrey Saxena. Neural heterogeneity refers to the idea that the brain is composed of many different types of neurons, with different parameters that describe their behavior. Most neural network models currently do not account for this heterogeneity. This may be because artificial models do not need heterogeneity to perform the tasks that they are designed to do. Taking this idea to the extreme, one could posit that brain functions could be achieved without heterogeneity, which raises the question, why does it exist in the brain? In this presentation, I would like to explore one hypothesis, that neural heterogeneity may have to do with task compartmentalization. In the framework of continual learning, if the computations for certain tasks reside in different areas of the activity space, or are, in other words, compartmentalized, then those tasks will not interfere with each other in something like catastrophic forgetting. One way to achieve this compartmentalization may be to have a set of neural parameters that only work for a certain task. If task A can only be achieved at a fast timescale, and task B can be achieved at any other timescale, then maybe this leads to a sort of compartmentalization in which task A is performed only by the fast neurons, and task B is performed by any other arbitrary set of neurons. To test this idea, I'm using a recurrent neural network that has a tunable time constant. The time constant ranges from 0 to 1 and represents the sensitivity of the neuron to input. A time constant near 0 represents a neuron that is slow to react to a stimulus, and a time constant of 1 represents a neuron that will instantly react to a stimulus. This way, we can design a network that is composed of two types of neurons, slow and fast. The tasks both require the network to generate a periodic function given a constant stimulus, as you can see on the left. The tasks differ in that task 1 is to generate a sine wave with high frequency, and task 2 is to generate an approximation of a square wave with a low frequency. These tasks were chosen in order to establish a distinction in the performance of different time constants, which the following figures will demonstrate. These figures were generated by training repeated instances of a homogeneous model on each task, individually to determine the best time constant to use for each. So a homogeneous model has the same value of tau for the entire network. As you can see on the right, the sine wave can really only be performed by the faster time constants. The time constants of 0.1 and 0.2 do not have consistent good performance. But the square wave can be performed reasonably by any time constant. The same time constant 0.2 generally has consistent good performance. So in our heterogeneous network, half of the nodes will be initialized with a slow time constant of 0.2, and half of the nodes will be initialized with a fast time constant of 1.0. Once the heterogeneous model is trained, we can examine where the tasks are stored in the model weights using the orthogonality of the neural trajectory and the performance of the model after having certain regions lesioned. For example, if the square task is stored entirely in the slow region of nodes, then if we remove the slow region from the network should no longer be able to perform the square task. In this analysis, the slow region was lesioned, corresponding to the nodes 0 to 10. You can see on the right that the squares indexed by the numbers 0 to 10 have a sort of muted color to them. This lesioning was performed by multiplying the weights of the slow region by 0.2 to diminish their influence on the model. Here is the model performance before and after lesioning. In all plots, the model's output after training is shown in blue, labeled model, and the target output is shown in orange, labeled example. As you can see, after lesioning, the ability to perform the square task is lost, while the sine task is retained. This suggests that the tasks are performed entirely by separate regions, despite not having placed an explicit learning constraint on the model that enforces this separation. Again, here we can see that the neural trajectories are relatively orthogonal to each other. The sine trajectories move mainly in an up and down direction, whereas the square trajectories move mainly in a horizontal direction. The fact that this separation occurs may be promising in continual learning. If different tasks are stored in different regions during the learning process, then catastrophic forgetting may be avoided. This can also be achieved without learning constraints, which are seen in the current literature. One major limitation is that the time constants were chosen in order to be optimal for the task at hand. What if we didn't know these time constants a priori, say in a network with a completely random set of time constants? Would the same compartmentalization be observed? This concludes my presentation. Thank you to my professor, Dr. Saxena, for her guidance throughout this process. And thank you for listening.